Hey students, this is a lecture on section 14.5, which is about directional derivatives. In order for this one to make sense, make sure you've already studied the other topic from 14.5, which is gradient vectors. Okay, so what are directional derivatives? The basic idea is you've got some function f of x comma y comma z. Here I have it kind of drawn as like it sort of looks like a mountain range. That's our function f of x comma y comma z. It's moving around in 3 dimensions. The directional derivative in the direction of vector A is going to be the same as the rate of change of this function f in that direction. So I know that looks complicated, but it's actually not too bad to find. It turns out that in order to find this, you need to find the gradient vector and then take the dot product of the gradient vector with the unit vector in that direction, and that actually gives you your rate of change along the direction of A. Okay, cool. So what does that look like? Well, the directional derivative of a function f of x comma y comma z in the direction of vector A is written as capital D sub A of f, and it turns out the way you find it is you actually just take the dot product of the gradient of f and u. And you're actually going to be evaluating this at a point, but I didn't write that point in there because it's usually easier to just have the formula without writing in evaluated at the point p naught. Okay? And u is actually a unit vector in the direction of A, so that's going to be vector A divided by its length. Okay? So let's go ahead and do an example. Once again, because this is a long topic, I'll probably only be doing one example. Okay, so example. Find the derivative of the function at p naught in the direction of A. Okay? Find the derivative of the function at p naught in the direction of vector A. Okay? And they're telling us that our function f of x comma y comma z equals xy plus yz plus zx. Okay? Where our point p naught, this is the point that we're going to be plugging in at the very end of the problem. That's negative 3, comma 3, comma negative 2. Okay? And vector A is equal to 2i plus 9j minus 6k. 2i plus 9j minus 6k. So we need to find the derivative of the function at p naught in the direction of A. Okay, and we're going to be using this formula, gradient of f dot u. That's the directional derivative of f. And at the very end, we're going to be evaluating this whole thing at our point p naught, which people usually write as a vertical line, and then they write their p naught. Okay? But we won't be plugging in the point until the end. So let's start with the rest of this. These take a long time to calculate because first you have to find the gradient of f, and then you also have to find the unit vector, which is A divided by its length. Then you have to take the dot product. So that's a bit of work. So let's go ahead and start with the gradient of f. So remember that the gradient of f is the same as partial f partial x times I plus partial f partial y times j plus partial f partial z times k. Okay? Partial f partial x times I plus partial f partial y times j plus partial f partial z times k. That's our gradient of f. Okay? And here, let's start with partial f partial x. So the derivative of this function with respect to x means that y and z are constant. Okay, so for our partial f partial x, since y and z are constant, the derivative of xy is going to be just y. Okay, so here we're going to have y. The derivative of yz is 0 because yz is constant. And then the derivative of zx is going to be z. So we actually just get y plus z. That's for our first coordinate. So for our partial f partial x. And then for our partial f partial y, the other two variables are going to be constant. So that means x and z are constant. Okay, x and z are constant. So since x is constant and z is constant, the derivative of xy is just going to be x. The derivative of yz is going to be z. So we have x plus z. And then the derivative of zx, because x and z are both constant, that's going to be 0. Okay, so here we just have x plus z times j. Okay, and then for our third coordinate, for the partial f partial z, that means the other two variables are constant. So here that means x and y are constant. Okay? So if x and y are constant, then the derivative of xy is just the derivative of a constant, which is 0. So this first term becomes 0. The second term, since y is constant, the derivative of z is 1. So this second term is going to end up being y. It's y times 1, which is y. Okay, so here we have y. And then for our third term, x and y are constant, but z is not. So the derivative of z is 1, so we're left with an x. So this one's actually going to be y plus x. So that's y plus x times k. Right, so there we found the gradient of f. Okay? And like I said, at the end, once you've found the derivative, you do want to plug in your point P naught. Okay? So let's go ahead and plug in our point P naught. So the gradient of f evaluated at P naught means we're going to be plugging in, for our P naught, they gave us the point -3, 3, -2. Okay, so we're plugging in -3, 3, -2. Okay, so that's x, y, z. So here x is -3, y is 3, and z is -2. So plugging everything in, y plus z is going to be 3 plus -2. So we have 3 plus -2 times I. And then we have x plus z, which is -3 plus -2 times j. And then we have y plus x. So we have 3 plus negative 2. I'm sorry, y plus x is going to be 3 plus negative 3 times k. Okay, so all I'm doing there is plugging in x, y, and z into the gradient. Okay, so 3 plus negative 2 is 1. So for our first coordinate, we just have 1 times I, which is I. And then for our second coordinate, we have x plus z, which is negative 3 plus negative 2, which is negative 5. So we have minus 5j. And then for our last coordinate, we have y plus x, which is 3 plus negative 3, which is 0k. Okay? So 1 times I is just I. And for the 0k, we don't need to write that. So here our gradient is actually just going to be I minus 5j. And that's our gradient of f evaluated at p naught. Okay, so now we got our gradient. Now the next thing we need to do is, in order to use this formula, gradient of f dot u, we need to figure out what u is. So u is the vector a divided by its length. So here, vector a in this problem is actually 2i plus 9j minus 6k. Okay, so we need to find the length of a. So over here, let me find the length of a. So for the length of a, remember you take the square root of the sum of the squares. Okay, so it's going to be the square root of 2 squared plus 9 squared plus negative 6 squared. Okay, that's going to be the length of vector A. Okay, and then simplifying that, remember if you square a negative, it becomes a positive. So that becomes a positive 6 squared. So what we got here is 2 times 2 is 4, 9 times 9 is 81, and 6 times 6 is 36. So we have 81 plus 36 is actually 107, right? Oh, I'm tired. No, 117. Oh, well, I can't think because I'm tired. So why don't I use my calculator? 4 plus 81 plus 36 is 121. Oh, okay. Well, I should have been able to do that. But anyway, we have the square root of 121. And remember, 11 times 11 is 121. So that's going to be 11. Okay, so the length of A is 11. So now that we have vector A and its length, we can find vector U. Okay, so vector U is going to be vector A divided by its length. Okay, so plugging everything in, we said that vector A is 2i plus 9j minus 6k. Okay, so 2i plus 9j minus 6k. Okay, and then we want to divide by its length. Okay, so our length we said was 11. So we're going to divide this entire vector by 11. And then we're going to go ahead and distribute the 11 to each denominator. Okay, so what we got here is 2 over 11 I plus 9 over 11 j minus 6 over 11 k. So all I did there was I distributed the 11 to every single denominator. Okay, and that right there is our vector u. And notice with u, you don't actually need to plug in the point p naught because it's actually already a number. Because it's just a vector. So you don't have any variables here. Okay, so now we're finally ready to find the derivative, the directional derivative. So remember, it's directional derivative of f in the direction of a is given by the gradient of f dot u, and we're evaluating this at the point p naught. Okay, but we already plugged in the p naught, and you really only end up plugging in p naught in for the gradient of f. You don't have to plug it in into your unit vector u. So what we're going to be doing here is we're really just going to be taking the dot product. Okay, so the gradient of f evaluated at p naught was I minus 5j. So we have I minus 5j for our gradient of f, and then we're taking the dot product of that with u. So that's going to be dotted with 2 over 11 I plus 9 over 11 j minus 6 over 11 k. Minus 6 over 11 k. Alright, and remember when you're taking a dot product, basically all you do is you multiply each component and then you add them all up. So here that's going to be, this first component is 1. So it's going to end up being 1 times 2 over 11. And then it's going to be minus 5 times 9 over 11. And then it's going to be plus 0 times negative 6 over 11. Because remember, if you don't write the third coordinate k here, it's automatically 0. Alright, so multiplying that all out, we end up with 2 over 11 minus 5 times 9 is 45 over 11. So we have minus 45 over 11. Plus 0 times any number is 0. Okay, so we actually have 2 over 11 minus 45 over 11, which is actually negative 43 over 11. So we actually found the directional derivative of the function f in the direction of that vector a. Now what does this actually tell us? This tells us how fast this multivariable function, which I sketched as kind of like a mountain range, is changing in the direction of that vector a. And this is useful in physics because sometimes you want to know how fast some complicated system is changing in some certain direction that you're pointing in. And so you know the vector and you know the function, but you want to figure out how fast that function is changing. Well, this enables you to do that. That's what we just calculated. So it's pretty cool. It's a little bit out there, but it's fun.